going to be looking at polynomial division and a couple of theorems that will help us take polynomials that are of higher degrees and find the zeros or factor them. Our goal is to be able to graph things fairly easily by using a handful of tools. So let's go back and remember something that we learned back in the 4th grade that you don't use very often, but in this particular section, the concepts show up again, and it's long division. So if you remember, you would take the number that you are going to be dividing into, in this case 875, and the number that you're dividing by goes on the outside. So then we ask ourselves, how many times does 25 go into 8, which it doesn't? And so then we say, well, how many times does 25 go into 87? And that would be 3 times. Then we take the number, that 3 that we wrote, and we multiply by the 25, and we write the answer down below. So we'll put a 75 here. And then this is the key part to remember, is that at this point then what we do is we subtract. Now what this algorithm is doing is actually determining how many 25s there are in 870, right? Because that's what that number represents, that 87. And then we subtract to figure out how many, in this case, 10s we have left over. And so it looks like we would have left over a 2 here and a 1 here. Now, because this number 12 is less than 25, we know that we can continue. And that'll be a key feature of some of the things we're looking at later. Then we bring down the 5. And then we ask ourselves, how many times does 25 go into 125? And that is 5 times. And then multiplying again. The 5 gets multiplied by the 25. We have 125. We subtract, and we end up with 0. The remainder here is 0, and so we know then that 25 divides into that number evenly. We could kind of see that just by looking at the original, right? But what happens when we have something that doesn't divide evenly? Let's do this problem where we can see that 22 isn't going to divide evenly into 875. Following that same process, 22 will go into 87, not quite 4 times, right? Because 4 times 22 would be 88. So it looks like it'll go 3 times. 3 times 22 is 66. We subtract, and then we bring the 5 down. Now I need to figure out how many times does 22 go into 215. I think it's probably going to be 9, right? Because if it was multiplied by 10, it would be 220. So 22 times 9 is 198. And then I'll subtract here. Changes to a 9. I'm sorry, a 10. And so I'm getting 17 left over. Yeah, that makes sense. So just to kind of put these ideas together for what we'll need next, we know that 875 is 22 times 39 plus that 17 remainder. On this first one that we did, we knew that 875 was equal to 25 multiplied by 35, right? We didn't have a remainder left over, but in this one we have that remainder left over. All right, let's look at the same concept with polynomials. We have special names for each of the components in these types of problems. People don't tend to remember them, but the number that we are dividing everything into is called the dividend. The thing that we're dividing by, in the last example that was 25 or 22, is called the divisor. The quotient is what we end up with as our answer, and then potentially there's a remainder. And notice that in this example, they're all listed out as potential polynomials. Now, as far as the remainder is concerned, we keep dividing until we either get 0 for the remainder, or in this case, because we're talking about polynomials, the degree of that final polynomial here is less than the divisor. Then we know that we can stop. Back in the example we were doing here, when we ended up with a remainder, we know that we can stop because that number is less than the original thing that we were dividing by. If it were higher, we could have added 1 to the dividend up here, right? We could have added something else, or sorry, the quotient could have added, we could have had 40 instead of 39. So we always have to look to see whether we can continue the division process. All right, so I'm going to go through a couple examples of long division. Just bear with me, and what this is going to do is lead to a shorter process called synthetic division, which doesn't have us write out all the steps. This is going to look really similar to what we just did a minute ago. All right, we want to determine whether these things are factors, meaning do they divide evenly into the polynomial. So I'll start with the x plus 1 on the left. So I want to divide x plus 1 into x cubed plus 2x squared minus 5x minus 6. Right? And I'm going to follow the similar type of a process that I did with the example that just had numbers. But the only thing that I do differently is I start by looking at the very first term, the x, and I ask myself, what do I need to multiply to make that into x cubed? And the answer would be x squared, right? If I multiply x squared by x, I'll end up with x cubed. Notice that I write that x squared above the column where the x squared is in my original polynomial. Then I'm going to take that x squared and I'm going to multiply it by both of these items. X squared times x gives me x cubed, and I put that in the correct column matching up the degrees. And then x squared times 1 is going to be x squared, so plus x squared. Right, now here's the important part. At this point in division, what we do is we subtract the numbers. So I'm going to change the sign. These are both going to end up getting subtracted. So the x cubes are going to cancel. I have 2x squared minus x squared, so I have x squared. And then I bring down the next number, just like we did before. And then I continue the process. What do I have to multiply x by to get to x squared? And that would be plus x. And then I multiply that x by the x plus 1, and I have x squared plus x. And again, we're going to subtract both of these numbers. So I end up with a negative 6x, and then I bring the next number down. X multiplied by negative 6 will give me that negative 6x. Again, I'm always looking at this first term and this first term. So multiplying those together, I get a negative 6x minus 6 And because I'm going to subtract both of these, they change to plus, and I end up with 0 as a remainder. So that tells me that x plus 1 divides evenly into that original polynomial without any remainder. Let's look at this next one, x minus 3. Let's see if that one's going to work. X minus 3 divided into x cubed plus 2x squared minus 5x minus 6. X times x squared will get me to the x cubed. I multiply down and I get x cubed minus 3x squared. Again, I'm taking this number and I'm multiplying it by this. Then I'm going to subtract both of these items. So what ends up happening is that first term changes to negative and the second term changes to positive. And then when I combine these, I'll have a positive 5x squared. And then I bring down the next term, 5x. I'm always making sure I'm lining up the terms that match as far as their degree is concerned. All right, x multiplied by 5x will give me that 5x squared. So I have 5x squared and then minus 15x. This changes to negative and this changes to positive. So I have 10x minus 6. Then we'll put a plus 10 here. So then 10x minus 30. This is negative and this is positive. And then when I add here, I'm going to get 24. 24, right? So this does not divide evenly. And the way we could write this, if we wanted to, using that theorem that or that definition we had before, is x cubed plus 2x squared minus 5x minus 6 equals what I divided by, x minus 3, multiplied by the answer that I got, x squared plus 5x plus 10, and then plus the remainder. But the remainder, plus this 20, plus this 24, right? But the remainder has to be divided by this. So we write that as 24 over x minus 3, right? Strike that part. We're not going to use that yet. We're going to do that eventually when we start getting to conic sections. But for now, we're just going to have the remainder hanging out there. Now, we're not interested really in polynomials that don't factor evenly. We want the ones where the remainder is 0. So going back to this part here, this is actually useful for us because if we're trying to find all the zeros of that original polynomial, then what we want to do is take this quotient and see if we can break that down from that point. So if we looked at x squared plus x minus 6, we know that that's easily factorable, right? That factors into x plus 3, x minus 2. So I've been able to find all the zeros of my original. X cubed plus 2x squared minus 5x minus 6 is equal to that first factor that divided evenly, x plus 1, and then I found the other two factors, So I know now what the 3 zeros are for that polynomial, and I can use that for graphing. Now, one thing that's going to make this a little bit easier is that the idea with the remainder theorem, if I know that something divides evenly into something, then it's going to have a remainder of 0. And to take that a step further, if I take the thing that is a 0 and I plug it back into the original, I'll actually end up getting 0 as the output. That saves me a lot of time not having to guess about numbers and use this process of long division. If I plug something in and I see that it equals 0, then I know that that's something that's going to divide evenly. So let's go back and look at this example here. This was the original polynomial that we had. And we know that, or we found that this was a factor. So that means that one of the zeros is -1, right? So what those two theorems are suggesting is that if I plug -1 back into the original equation, I should end up getting 0. Let's check. -1 to the third power plus 2 times -1 squared minus 5 times -1, oops, minus 6. So this is -1 plus 2 plus 5 minus 6. Yeah, this ends up being 0, right? And the same thing would be true if we plugged in the other zeros, x equals -3 or x equals 2. This will narrow our search as we're trying to find zeros overall. All right. So rather than do synthetic division, we are going to, long division, we're going to focus on synthetic division, which is a shorthand way of doing problems where we don't have to write out all of the steps. So I'm actually going to do this problem twice, one with long division and then the second time with synthetic division, just to show you that it's a lot simpler. All right, so bear with me. This one's going to be lengthy. Actually, what I'll do is I'm going to pause and just do this and then come back and show you the result. I went ahead and did the long division, and you can see this one is extremely long. A couple of things to take note of. In the original, we had an x to the 5th power, x to the 4th, 3rd, 2nd, but we were missing an x to the 1st power right here. And so we add a placeholder. There's 0 of those x terms, so we write it as 0 times x to the 1st power. And when I need that because when I get to this stage here, when I multiply through, I need to have something to subtract from. And so that 0 times x is sitting there. This one doesn't divide evenly. We end up with -6 as a remainder. And so what I'm going to show you next is a process called synthetic division, which is a lot faster than this. But I wanted to have this here for us to look at so we could compare the synthetic division version with the long division. So again, this is synthetic division. And what we're doing is the same process that we had for long division, but we're not writing any of the variables. So originally what we had was, let's see if I can copy this and paste it. I don't know if it'll let me. It won't let me. Right, hang on. -4x to the, I think, 5th, right? -4x to the 5th plus x to the 4th plus 6x cubed plus 2x squared plus 50. I'm going to put a plus 0x and then plus 50. divided by x minus 2. Let's double check. Yeah. When you use synthetic division, one of the things that you do that's different is you use the 0 rather than the divisor. So the 0 here is x equals 2. So I'm going to put a 2 here. And then I'm going to just copy all of the coefficients from the original polynomial. So I'll have a negative 4, a 1, 6, 2, 0, and 50. Again, what I'm doing is I'm looking at the original and I'm copying the coefficients, a negative 4, a 1, 6, and so on. All right, then I'm going to draw a line underneath this. The first number comes down, so we'll put a negative 4 here. And then I'm going to multiply these two numbers and write the answer in this space. So multiply those two numbers, I get a negative 8. And this is a slightly different modification. When we go down, in this case, in the columns, we add the numbers. In long division, we end up subtracting. So make sure that you add the numbers down. So negative 8 plus 1 is a negative 7. Then again, I repeat, I'm going to take this number here and I'm going to multiply it by this one and write the answer here. So 2 times negative 7 is negative 14. And then I add down 6 plus a negative 14 is negative 8. Multiply again to get negative 16. Add down to get negative 14. Multiply to get a negative 28. Add negative 28. 2 times negative 28 is negative 56. Add down and I get a negative 6. So what I want you to look at is in synthetic division, this part tells us what the quotient ends up being. Let's look back at the original that we had. There's a negative 4 and then a negative 7. Looking back up here, that's what we had up here. We had negative 4 x to the 4th, negative 7. Those numbers match, and the thing that is happening is that because we started with something that was x to the 5th power, now our quotient is x to the 4th power. But the numbers that we get down at this bottom of synthetic division are the coefficients of the terms, negative 4 times x to the 4th and negative 7 times x to the 3rd. This will be the x squared term. This will be the x to the 1st power term. This will be the constant, and then the remainder is 6. If we look back up here, our remainder was negative 6. So what we're going to do is use a combination of the plugging something in to see whether it's a 0 and then synthetic division to factor things down into smaller components. All right, let's do this example using synthetic division. Again, when you use synthetic division, what you plug in on the outside is the 0. So the 0 here is going to be x equals negative 3. So that goes on the outside. Then I write the coefficients of the original polynomial, 2, 7. I have to put a 0 placeholder because there's no x to the 1st power term, and then negative 5. The first number comes down, and then we multiply and write the answer under the next column. Add down, and then multiply again. Add to get negative 3. This will give me a 9, and so it looks like my remainder here is 4. So x plus 3 does not divide evenly into that original. Using that factor theorem, what would happen if I put negative 3 into the original? Let's see what happens if we do that. We would have 2 times negative 3 cubed plus 7 times negative 3 squared minus 5. So that's, let's see, negative 27 times 2, right? Negative 54. And then this will be 9, it'll be plus 63 minus 5. Plug those into the calculator, and we get 4. And that's not a surprise. The number we get here is the same as we get here. So the process that we'll use is, if we want to see whether something is a factor or divides evenly, we'll plug that number into the original, and if we get 0, then we'll use synthetic division to break the polynomial down further. If we don't get 0, we're not going to use that because it's a waste of our time. Let's determine whether 5 is a 0 of this. So what we'll do is we'll plug in the number 5 to the original. And if we get 0 as a remainder, 5 is a 0 of the polynomial. So 5 to the 4th power, 625, 26 by 25, 650 plus 25. Yeah, it looks like this is a 0. So because this divides evenly, I'm going to use synthetic division to break this polynomial down further. So 5 is a 0. That means that x minus 5 is a factor. So for polynomial synthetic division, we'll use that number 5, and then we'll take the coefficients, 1 for the x to the 4th power, 0 because there's no x cubed term, negative 26, another 0 for x to the 1st power, and then a plus 25. Bring the first number down, multiply, and add. Multiply and add. And as we suspected, we end up with 0 as the remainder. But the reason we use the synthetic division is because now we know that the polynomial can be broken down to x cubed plus 5x squared minus x minus 5. So looking at my original, x to the 4th minus 26x plus 25 is equal to x minus 5 was the first factor we found. And then the quotient that we just found using synthetic division is this. This looks like one that we can factor by grouping, doesn't it? So let's continue. We can have an x squared times x plus 5. And then if I take out a minus 1, I'll have an x plus 5 also. And this x minus 5 is kind of just here along for the ride. So then I get x minus 5. Inside the brackets, we've got x squared minus 1. Putting this and this together. And then I have x plus 5. X squared minus 1 factors to x plus 1, x minus 1. So it looks like I was able to find all 4 zeros of that original equation. We know there would be potentially 4 because it was raised to the 4th power. Now, just to kind of talk about some ideas we had in the last chapter, let's redo this problem a slightly different way. X to the 4th minus 26x squared plus 25. The way that we factored this before was we did a variable substitution. We said let's say m equal x squared. So then m squared is equal to x to the 4th power. So I could rewrite this as m squared minus 26m plus 25, which factors into m minus 25 and m minus 1. This is something that looks like follows the same patterns of a quadratic, even though it's not a quadratic. And this gives us, changing back to the original variable, I have x squared minus 25 and x squared minus 1, which is x plus 5, x minus 5, and x plus 1, x minus 1. Again, this is just a different way of getting the same answer that we got before. These two answers match, just two different techniques. If we're able to factor something easily, we do that, but more often than not, we end up with something that we don't know how to factor. And so we use this idea of synthetic division to break down to a smaller degree polynomial so we can continue from there. All right, so here's an example that we're more likely to see where trying to factor this by grouping doesn't end up working. And so we have to try to use a different method. In the next section, what we'll do is we'll talk about how to know what numbers to potentially test. So I'm just going to start guessing and checking. I'm going to guess x equals -1, and I want to see whether that's going to divide, if that's going to be a 0. And I do that by plugging it into the original. So -1 cubed minus 3 times -1 squared. And if I end up getting 0 here, I know that x plus 1 in this case would be a factor. What's this? -1 minus 3 plus 6 plus 8. No, this is not going to be equal to 0, right? So that means that -1 is not a 0. Let's try 1 instead. We always want to try -1 and 1 first because they're easy to plug in. So we get 1 minus 3 minus 6 plus 8. Yeah, that equals 0. So that means that x equals 1 is a 0. So now what I'll do is I'll use synthetic division to break that polynomial down further. So I'll put 1 on the outside, and then again I use the coefficients of the original. So 1, -3, -6, and 8. Bring the first number down, and then multiply, add, multiply, add, and as we suspected, we get 0. But the reason we did this is so that we can see what the broken down polynomial is, which is x squared. We always go 1 degree less than the original, right? The original was x cubed, and so we go to x squared minus 2x minus 8. I know how to factor that. That's x minus 4, x plus 2. So our original, x to the 3rd, minus 3x squared minus 6x minus 8 factors into x minus 1, that's our original that we had right here, times x minus 4 and x plus 2. Just remember that when something is a 0, that the factor, we have the number written in the opposite way, right? X minus 1 means that that positive 1 is a 0 for that. So this is the complete factored version, and we know then that the zeros are 1, 4, and -2, and we can use that for graphing. All right, look for the next video that talks about how to determine what numbers to guess. Have a great day.